All right, we're gonna do a lesson set 6, I believe. We might even continue. Well, let me show you what lesson set 6 is. For the most part, I've decided to put all the problems on the board here and then kind of chip away at them, moving from right to left, erasing the board as we go. You can pause the video and try these problems. So take maybe a pause right now. And then there's another section over here of problems on a movable whiteboard, and I will center that a little later. All right, so I'm gonna do each problem, maybe talk a little bit about each, and you can kind of move the video to wherever you think you need work. I see that these lights sometimes cause problems. So this problem here is -4, -2. I'm gonna have to rewrite it over here. -4, -2 to 6, 5. How do we write that equation of a line passing through those 2 points? I don't like the y2 minus y1 rise that's in the textbooks. I asked the question, how do you get from -2 to 5? I think that's easier. The brain works a little easier. -2 to 5, 7 units of change. -4 to 6, 10 units of change. And then all we have to write is x plus 4, so that when you drop -4 in, the multiplication becomes 0, and you get an answer of a y value, -2. Get an eraser here. Let's erase that. Well, if we can, I think this question here, I better look. Slope intercept form. All right, so slope intercept form. We will go to the mx plus b. I like to say ax plus b, but -3/5 x. Distributing, minus times a minus is a positive 6/5. And 5 times -7 is -35 over 5. And that's how you can get the numerator of that last fraction quickly and easily. So what does this become? 6 minus 35 minus 29/5. That becomes -29 over 5. All right, so that was problem number 2. Problem number 3. You see this all right? Yeah, pretty well. If we can write the equation of a line from 2 points, we should be able to find 2 points quickly. We want 3, but 2 gets you -8. 2 makes the multiplication here 0. -8 gets me -8. We're changing by 4, so that's a 6. Why don't I just keep going? 10, 14, 18. I'm always changing by 4. That's the linear process. And I'm going down 9. -17, -26. Let's put a 10 in. Should get a multiple of 4. 10 minus 2 is 8. 4 goes into 8 twice. That means I'm dropping down 9 twice. Once, twice. Yes, it does produce -26. I don't like dividing by negatives. I'll bring the 2x to this side, 10x, add 4 to this side, 9, and it sure looks like 9/10 is my x value. It's helpful to have a picture in your mind about what's going on. This is a linear function, -2x plus 5 in the ax plus b format. +5, the y-intercept going down 2 over 1. I get a quick feel for a decreasing function. -4, if that's 5, -4 is maybe there. I'm going over 1 up 8, so it's a pretty steep rise. Pretty steep rise should have gotten me an x value that was small but positive. I think it was 9/10. That tells you what my memory is here. Yeah, well, I could have done the equation again. Same thing here, but let's explain this one a little bit. Students have trouble with this, and I didn't copy it correctly. So it should have been 7x over 5. There. And these mean the same thing. I'm multiplying by it and then dividing. Multiplying x by -3 and then dividing by 2, or dividing x by 2 and multiplying. The order doesn't matter. But I could have put the x in the numerator or along the division bar. Okay, but don't put it in the denominator and think you have a linear function, because you don't. Okay, so be careful how you write this. All right, let's start with stuff we know. 1 plus 2 equals 3. It is also true that if I multiply every single term by 10, I get 10 plus 20 equals 30. Now, I could have expressed the number 1 as 5 divided by 5. And I could have expressed the number 2 as 4 divided by 2. Let's see, do I want that? 6 divided by 3. No, I do want 4 divided by 2. All right. So now what happens when I multiply? Well, I don't think I have to say 50 divided by 5. I don't think I have to do that, which is 10. I think it's easier to say 5 goes into 10 twice, and 2 times 5 is 10. We'll see it a little more easily here. 10 times 4 is 40, divided by 2 is 20, but so is 2 into 10. 2 into 10, 5 times 4 is 20, and then multiplying by 10 gets me 30. So you try that problem now. You should be doing that anyway, I hope. Pausing the video. I'm not going to keep reminding it. All right, so I am going to multiply. What do 2 and 5 have in common? They've got multiplication, but they're the factors of 10. So 2 goes into 10. 5 times negative 3 is minus 15x. 10 times negative 5 is minus 50. 5 goes into 10 twice. There's 14x, and 10 times minus 6 is minus 60. I'll bring the 15 to the right, there's 29x. I'll bring the 60 to the left, there's 10. It looks like my x is 10 over 29. I have a little Freudian activity going here. I like small positive numbers as answers. Let's show why. Go back to the original, minus 5. We'll call that minus 5. Going down 3 over 2, down 3 over 2 looks a bit like that. Minus 6, well, there's minus 6. Over 5 and up 7. Oh boy, yeah, that's a small positive number there. Just to the right of the y-axis. That's problem 6, I believe. Maybe it's 5. Yes, it was 5. So, perpendicular to this line equal to 257. If you look at your answers, and I'm passing through a point, I forget what point it was. It's on the sheet here, so I might as well give you what point it was. 9, 2. If it's 9, 2, then x minus 9 plus 2, and that's my function. Okay, and you should look at the original. Say, oh, God, I wonder how I could possibly get that answer each and every time. Well, let's show the work. First, we have to find the slope here. Doesn't look like 257 has anything to do with this problem. So let's just move the 3y to the other side. Let's leave the 2x here, and I can see y is coming from 2/3 of an x value. That's basically what's going on. Okay. So if this is doubling something, right? Well, I could talk about it a little bit more, but I think we'll just keep going. All right, so over 3, let's call that 3, and up 2, that looks to me like a 2 to 3 ratio. That's the original. That's the original. We want the perpendicular. The perpendicular is going down. Let's go from some location. Let's go over 2 and down 3. Over 2 and down 3. Does that look like it's forming a perpendicular? Picture's worth 1,000 words, as they say. Yes, it does. So that takes care of that. F of x equals 5/3 x plus 7, and we want to do f of negative 2, so we're plugging negative 2 in for x. Can this be seen? Yes, plus 7. That's minus 10/3 plus 21/3. Hopefully you can see how you can get a little quicker as you keep practicing. So 11/3. Doesn't look like negative 2 should get us 11/3. Let's graph it. Over 0 gets you 7. That's a multiplication here. Make it 0. 0 gets you 7, and we're going to go over 3 and up 5, something like this. Negative 2, does negative 2 look like it gives us, I forget what the answer was, positive 11/3. So that probably would have been in here if I put some numbers in. Okay. All right, so that didn't help too much, but f of x equals 5. If a equals b and b equals c, then a equals c. So f of x equals 5x plus 7. Then f of x could have been written as 5/3 x plus 7. And we set it to 5. That gets us negative 2. That gets us negative 6. That gets us -6/5. Okay, just using inverse operations. All right, that takes care of that. Let's move this over a little bit. Let's do the next line of work. -3/2 to the what? Well, I see that I have to flip. I've got to flip this fraction, so the minus sign does that. All right, so now I have -2/3. How do I turn -2/3 into -8/27? Sure looks like I have to do some cubing. So my answer was -3. What's the quickest and easiest way to take the square root of 63? It's to say the square root of 9 times the square root of 7, which is also equal to 3√7. I do not know the square root of 7 as an approximate decimal, so I'm not going to try to tell you what it is. So I'm just putting problems up that I've seen wrong in my calculus classes, students coming in and making mistakes. So that's what's on this worksheet, all the problems that I've seen. Okay. So a lot of times people cancel something and I don't know. But anyway, if you are going to take 6 + 4 and cut it in half, what you're basically doing is cutting in half 6 + 4. And you would distribute that multiplication, which means that there's really a distributive property of division. Hope I can say that. So this fraction should be written as two fractions, 4x/10, 4x to the 10th divided by 8x to the 5th, and also minus 12x is being divided by 8x to the 5th. Now it's just a question of counting factors. X to the 10th is really x to the 5 times x to the 5. Well, I don't have to multiply something and then divide it by the same number. That seems foolish. So x to the 5 goes into x to the 5 once, doesn't disappear, it's a 1, but the 1 disappears in the multiplication. So that became 4x to the 5 over 8. So there's 4 more x's in the denominator. This could have been x times x to the 4th, x to the 5th. So 12/8 is what? 3/2. Divide each by 4. And I can see that there's a 1, which gets multiplied times the 12 and disappears. And that's your answer. All right, so now each time as we do create these lesson sets, at midterm, get a whole nother batch of 55, but maybe just some of them are similar, but the level of difficulty continues to increase. So here's a little more challenging radical expression. I'm going to write √10 as √2√5, and that's the one I'm going to multiply. No, I'm not. I'm going to multiply that one by √10 times √10√2. Right? That is another way of writing this. Then I am going to add. I'm going to call √10 √2√5 times 2 times √6. I'm going to call √2√3. I think that's the quickest way to do this in your head. So this is 10√2, which I hope people know is about 14.1. Asking people to memorize that, but folks tend not to, so I just keep saying it, make it happen. Now I've got √2 times √2, which is 2. So maybe I'll slash that. It's taken care of. And I've got another 2 here. So I'll take care of that. And √5 times √3 is best expressed as √15. So my final answer, 10√2 plus 4 √15. Okay, and we'll probably have to practice these for a while. What I usually see, it takes students a while to get those right, but we will. We'll just keep doing it until we get it right. Okay, so making sure you know your rules of exponents. So how many more are where? I'm not dividing 20 into 40. I'm really saying m to the 20th times m to the 20th. Okay, so 40 minus 20 is equal to 20. And to the -3 is the same thing as 1 over m to the 60th. We generally like to express negative exponents as positives. And so that's what that equals, which is also equal to m to the minus 60. I mean, it's not wrong, but I'm preferring that. X minus 4 times what? Gets me x squared minus 2x plus 11. So that's the problem we're working on right now. And I think we can see pretty well, but the light does give some streaks on the board. Okay, so my calculus class, students would, I've never had anybody get this problem the first time they've seen it. And that's a shame, because you can rename that easily and then the folks can do the calculus work. But this is a precursor to the long division. And a lot of folks do this in Algebra 1 and wonder why. Well, let's just get an answer just organically. X times x is x squared. Well, we do a lot of FOILing. I think we need a positive 2 to get that middle term. And if you multiply this out, you've got x times x, x squared minus 4x. We got to get from minus 4x to negative 2x, then we better go up 2 x's. There's the FOILing that goes with that. Now minus 4, so right now I have this. And I also have minus 4 times 2, which is minus 8. But I want to get to 11. Well, I think I need to add 19 units somehow. But I sure as heck don't want those 19 units squared multiplied by x minus 4. So I go up 19 units and I take away that multiplication. And if people knew how to do that, then if I asked students to give me the integration of x plus 2 plus 19 over x minus 4, usually get right answers from students in a calculus class with enough practice, obviously. But it's the foundation that gets in the way. So we're going to practice that. There was no reason to come over here and x times x is x squared, x times minus 4 is minus 4x, and then you got to remember to put a minus sign, which always seemed cumbersome to me. So if we're doing long division, we're going to say x times x is x squared, change the sign and add. We're going to put as we go. X times minus 4 is minus 4x, change the sign and add. That gives us 2x plus 11. How many times is x going to 2x? Twice. 2 times x is 2x, change the sign and add. 2 times negative 4 is negative 8, change the sign and add. And there's your remainder of 19. That's an easier way to do long division. So I'm not going to teach it. I want us to practice this process. So that's where we're going to put our time. All right, so that's gone now. You can always check to see if you're right in your long division, because that 19 could have gone outside, right? Could have gone outside the parentheses. Easier to see if it's outside. And then we have a calculation that we're saying is equal to another calculation for all numbers. So what number would be easy to pick? 4. So if you picked up 4 on the left, you would get rid of the multiplication and you'd get 19. So if I put a 4 in here and I don't get 19, I got a problem. I got 16 minus 8 plus 11, which is 27 minus 8, which is 19. Boom. So if you're on a test, you don't have to ask your teacher if you got it right or wrong. Check it yourself with a number. I could have put some other number in, maybe minus 2, right? But why pick something? Maybe 5, but if you put 5 in, it's just making the numbers bigger. So. All right, so next problem is a function, and we're evaluating f of x. No, we're finding the inverse. The inverse of f of x equals 5x minus 3. I'll show you shortcuts later, but f of x is another way of saying y equals 5x minus 3. And if you want the inverse of x to y, which is what we're doing, except dyslexically, it would be nicer if you put the y over there. If we're doing x to y, then the inverse is y to x, which means that I'm switching my input. I'm switching my input to the letter y, and I'm got my output now as x. That's the inverse. Now, to make this a function, we have to solve for y. So I think we can see it here. You got to add 3 and then divide by 5. Okay, so that is the notation for inverse. What's the inverse of the sine of x? You haven't even studied it yet. It's sine inverse of x. Over here, you go from angle to ratio. Over here, you go ratio to angle. Okay, just planted a seed. So our inverse is, if you had a number here, how would you solve it? You'd add 3. So that's my generic number solving and divide by 5. Let's put a number in. Let's put 10 in. 50 minus 3, 47. 10 gets you 47. Well, let's put a 47 in this one. 47 plus 3, 50 divided by 5, 10. I think I see some inverse relationships. All right, so that problem 15 will take time. However, if you know what you're doing, then you just write it on your answer key. We don't have this discussion, but we got to learn how to do it first. All right, so I see 0. So I see x squared minus 6. I could have written x minus 0 squared minus 6, okay, to follow our form. But it's nice if you can recognize a vertex and a graphing form when it's not showing the minus h. Okay, so how do you get from minus 6 to 1? You go up 7 units. 0 to 10 is not linear change, it's quadratic change. And 0 to 10, if I'm looking at quadratic change, I'm looking at the area generated. And that's 100. All right, so that's that function. Because when I put 10 in, it's got to get me a 1. So I got to convert squared units. Number 17. P of x equals log base 7 of x. Be nice if I knew what I asked. Find the inverse. Okay, so what's the inverse? Not f, because it's p of x. P inverse of x. Oh, if you're pausing the video, you'll hear me say in class repetitively. What's the inverse of exponentiating? Logarithmic activity. What's the inverse of logarithmic activity? Exponential activity. So this is 7 to the x. Let's check it. Let's look at log 7 of 49, which is 2. Is that the same thing as 7 squared equals 49? Think of 49. This x gets me that y, and over here, this x gets me that y, and I think that they are inverted. 49 to 2 becomes 2 to 49. That's the inverse. So if I'm solving a 7 to the x equation, and I want to know when the 7 to the x equals 48, then x is equal to the log base 7 of 48, and you need a computer or a calculator. And I will show you how we used to do it with change base formula about a month and a half from now. We got a lot of work to do before we get there. It's easy to get an answer, but seeing why, that's another matter. We'll get there. All right, so log base 125 of 25 is asking the question, 125 to the what equals 25? Well, we don't have any exponential rules unless we have the same base. 125 could have been written as 5 to the 3 and 5 to the 3 to the x. I'm going to skip that step from now on and cut right to writing it that way. And 25 is 5 squared. So therefore, 3x has to equal 2 and x equals 2/3. So I got some cube rooting. And then I'm doing some squaring. And what am I working on? I'm working on 125. So what's the cube root of 125? 5 squared, 25. You can always play it again, especially if your name's Sam. A squared minus 8a plus 7. We're just doing some basic algebra 1 factoring here. A minus 7 times a minus 1. Okay, the foiling. If you're going to get a middle term that's negative and a positive end term, then it's got to be a minus minus. Just remember that. Number 20, big question mark. Why? Find the quadratic roots given. Oh, I haven't checked my answer key, so this will be different from what may be on your test, but I'll just make something up. Let's say A is 9, and let's put a 7 in here, and let's go to roots. Well, roots are zeros, and I've already constructed this. So let's say that, so A equals 3. How's that sound? Now let's make A equal 2. Okay, but I got a cup shape up, vertex 9, 7, then the roots are as follows: 9 plus or minus the square root of 7 halves, and you're imagining things if you think that cuts through I to 0. Okay, but I have to move down 7 units. I'm multiplying by 2, so division. So once again, you're new to this. So I could have written this in the A x minus h squared plus k form, and I'm setting that to 0. I've been given A, I've been given H, and I've been given K, which means I've basically been given a gift. Inverse operations, minus 7 over 2, minus 7 over 2 plus minus the square root of the minus outside. Set minus 9 to the other side, positive 9, and we might as well show it one more time. Let's show that answer. 9 plus minus the square root of 7 halves I minus 9 squared times 2. Let's do the math. The 9's cancel. Squaring a plus minus gets you positive. Squaring a square root gets you what's inside, and squaring I gets you I squared. 7I squared is minus 7I, minus 7 halves. The 2's cancel, and minus 7 plus 7 gets me the roots. Okay, moving right along. 7 minus 2, 3x minus 4 squared. We're hopefully getting a lot better with the squaring of a binomial. Minus 2 times 9x squared. Double that product, minus 24x. Square that, plus 16. Bring the positive 7 to the end. That's the last thing we're going to do is that 7 minus 18x squared plus 48x. Minus 32 plus 7 is, I believe, minus 25. Okay, moving right along. Making sure we can see the next column of work. 3x plus 8y equals 48. So I guess I'm asking, I gotta move this down a little bit. I think I'm probably asking for the x and y intercepts here. Graphing this, what's the easiest, quickest way? Cover up the y's and you got the x-intercept at 16. I should have taken more time with this because I know I'm going down, standard form going down, so I should have put the 3x plus 8y equals 40. I should have put the 16 here so that it doesn't get in the way of my drawing. I've got 8 into 48, 6, so I've got a 0, 6. I'll put that above, and now I can see my line by just using zeros. Remember, 3x is 3 times x. It's a product. I know we just say it's a term and a linear term, but it's a product. And setting products equal to 0 can yield easy information and quickly. Anything times 0 is 0. So plugging in 0 gets me 6, plugging in 0 for y gets me 16. X and y intercepts. That's what standard form is all about. And we can use that standard form for other situations similar, but not linear. Look for that as we continue. 4a squared minus 19a minus 5. You know, there's possibilities here of 2a, factoring this, I'm assuming. There's two possibilities. There's 4a and there's a. And you just got to be a Rolodex here. You got to roll all the possibilities. So I can see 5 times 4 is 20. So I'm going here right away because I want 19. And so that's got to be 1. So it's not so bad. Minus plus. Okay, but you got to consider your possibilities. There are ways, factor by grouping, but I'm not going to teach that. Just practice the, getting better at just calculating. All right, so You've seen this now for several days. I hope you're not doing any work. It's a product. What do? Each term, we make each term 0. So how do I make 5x equals 0? How do I make 2x plus 5 in the parentheses equals 0? Because I don't care what number you raise it to if it's 0, right? And how do you make 7x minus 1 equals 0? I hope you don't have to take pencil to paper. I hope you can see 0 minus 5 halves and positive 1/7. All right, go ahead and solve this. 7x minus 1 equals 0. What are you going to do? Inverse operations. What's the inverse of subtraction? Additional one. What's the inverse of multiplication? Division. Okay, keep an eye out for that. Okay, now I'm looking at a quadratic and I'm looking for the minimum value. So the minimum value is k in the HK, and we have in cup shape 4x squared plus 16x minus 5. That's a cup shape up. So H we need to find, and K is our answer. That's the minimum value. It also is the range. Greater than or equal to K is the range. I haven't mentioned range yet this term. I just did. All right, so that means we're going to start putting it on test soon. 4x squared plus 16x minus 5. Why did I erase it? I don't know. I'm getting used to erasing things. So minus b, 16 divided by 8 is 2. That wasn't so bad. All right, so let's make sure we have the right one by plugging in 2. So 2 squared, that's 16 minus 32 plus 5. I see the 2-to-1 ratio. I know I'm right. So minus 16 plus 5 minus 11 is our answer. That's the minimum value. You cannot get a y value out of this calculation that is smaller than negative 11. Not possible. Why? Well, it was 4. Let's put it in graphing form. X minus 2 squared minus 11. You put any other number in here besides 2, and you got, I don't care, minus 5. What's minus 5 squared? It's positive. What's positive 5? Positive. You have a positive influence on that number, which means it's going up. With acceleration, too. All right, f of x is, so the y-intercept, 3 log x plus 9 plus 5 base 3. And I want the y-intercept. Well, y-intercept. Here's the y-axis. Here's 0, 0. Here's friendly number 0, 1. Here's friendly number 0, negative 7. I see a pattern. I see my x's are 0. So I put 0 in for x. What's the exponent you put on top of a 3 to get a 9? Well, that's a 2. 3 times 2 is 6 plus 5 is 11. So 0, 11 is your y-intercept. There. F of x equals 2 to the x, g of x equals 2x minus 7. Yep, you can see this. F of g of negative 3. F of g of negative 3. I continue to say it. That's the same thing as f of g of negative 3. And that's how the SATs like to give you a composite. So you have to do g of negative 3 first. So plug negative 3 into the g function. And that gets us 2 times negative 3 minus 7, which is negative 13. We take the negative 13 and we plug it into the f function. 2 to the negative 13th. 1 over 2 to the 13th. Don't know why I gave you that particular number, but I did. So 2 to the 13th, I do not know. 2 to the 6th was on the last test. That's 64. So you got to square 64 and then double it. I don't know what number that is. You can get a feeling for it. When does f of x equal 1/16? Well, 2 to the x equals 1 over 16. I think I have to write 16 as a base 2. Otherwise, I can't use rules of exponents. So 2 to the x equals 1 over 2 to the 4. And if I want 4 factors of 2 in the denominator, I better make x negative 4, because that communicates that you're doing this operation in the denominator, reciprocating. All right, that was that one. All right, now I can bring this forward to the other side and continue that process. Name that tune. I don't know what tune I gave you, so I'll give you. I'm not sure what's gonna show up on the test, but I'll give you a tune to name. We've been practicing writing exponential functions. So why don't we do a decay? Let's make this 20. Let's make this in 1803. Let's say that we had more than 20. Let's say we're up to 35. Right up there, okay? And then let's come down here about a third of that. So let's get close to a third of that. So that's, oh, well, that is nice. I have that answer. That's 25. Okay, and let's put that at 1900. And so we're doing this and we are hoping to see 1/3 to the x base. Now, where does the base of an exponential function come from? Differential 2 divided by differential on a right, differential on the right, divided by differential on the left. What are the differentials? Well, how do I get from 20 to 35? Got to go up 15. How do I get from 20 to 25? Got to go up 5. What's the differential on the right? 5. What's the differential on the left? 15. That's why I knew that. So now let's write the equation. The most important y value is 20. My first jump is 15. My next jump is 1/3 of that. And 1803, let's use a T. T 1803. And how long did it take for that to happen? 97 years. I don't have a physical context for you, but that's name that tune. Now, I'm not sure which one I'm putting on this lesson set, which is a test for my class today. 60, 70 minutes. They got to do all these problems in 70 minutes. So number 30 is also a name that tune. Okay, well, this was on the last test. 5-7 wasn't exactly this problem, but it was this process. Let's make this 11, how about -9? All right, there we go. So that's the inverse of a parabola on the one of the branches. And so we are now looking at a square root of x minus h plus k form. And therefore a is the rise over the square root of run as measured from the endpoint. So what's the rise? From 7 to -9, -16. What's the square root of the run? Well, from 5 to 8 is 11, so that's square root of 6. 5 to 11, 6 units, and I'm doing the square root units are being canceled, so I've got x minus 5. Square root units are now canceling, and I really get a rise over run. And I want to get from 5 to 7, and I add 7, and there's my calculation. And I'm hoping that folks don't need explanation from this much longer. They can just write it on the answer key without having to do any work. So we don't want, we don't want to make a thinking mistake. If we don't want to make a thinking mistake, we don't want to think. Well, that's an interesting proposition. Yeah, how many times have you heard don't think? I don't know. So now that takes care of these. So now I'm doing log x base 5. Here. Maybe if you just take a gander at that and write those problems down, then I can just look over and copy them on the board because this is getting awkward. So log base 5 of x. I got to turn this. So we are now doing log base 5 of x equals 0. You always want to do the inverse operation here. The inverse operation is quantity to exponent becomes exponent to quantity. 5 to the 0 is 1. So I'm really hoping that you get used to this 1 in here, getting you that number, because we're going to do multiplication and addition. That's what we've been doing with most of the functions that we've been writing quickly and easily. We've been creating zeros and ones. 7x squared plus 30 equals 5. Can you see this function? Can you see the picture? We talked about it half an hour ago. That's in graphing form. So the vertex is 0, 30. And you're going up pretty quickly. We want to know when we hit a 5. So we got imaginary numbers. And we got two answers. So minus 25 divided by 7 minus 25 over 7 plus minus the square root of a negative is imaginary. So 25 over 7. And then all we have to do is bring, oh, we're done. Because that was in graphic form. All right, so those are your answers. And you could have rewritten that as 5 over root 7, could have rationalized it. But we're just looking at the thought process behind getting a quick answer. X, Y, Z. So we're going to be graphing problems that have an X and a Y, and we're going to find Z. And Z is always going to be positive in our drawings, whether our X is in this direction, our Y is in that direction, and our Z is here. We're always going to call the hypotenuse a positive number. We're heading towards trig soon. We're getting our Pythagorean theorem down. And once we do, then we're talking sine, cosine, and tangent, and then we're going to expand upon that. And we're going to learn how to graph those quickly as well at this level. We're going to do the unit circle, so a lot's coming. So I have a Y of 5, a Z of 9. So that looks about 9. That looks about 9 to 5. Somewhere in that looks like a decent picture. Not the greatest, but okay. So I'm going to go with that. So how do we do this problem? Well, we find 81, we find 25, and then we look at this and we say, 56. And so we want the distance here, and if that's a square, then that's the square root of 56. That's how we want to do those problems. I don't care if you simplify that, you know, 8 times 7, right? 8 times 7 is 4 times 14, I believe. So this is 4 times 14. Let me check that out. 40 and 16, yes. So square root of 4 times square root of 14. Square root of 56 could have been 2 root 14. We get a little bit more practice with something we're doing elsewhere. And then we're getting to that stage where I'm going to start making some careless errors. Hopefully not. I think I'm doing okay. Negative 4, 1 to 1, 4. What did I ask? Number 34. I have no idea what I wrote there. Oh, distance. Okay, so the distance from negative 4, 1. Negative 4, 1 might be about there to 1, 4. 1, 4 might be here. Negative 1, 4 over here. Negative 4, 1, sorry. Negative 4, 1. All right, well, can't I just do the same problem I did a minute ago and find the change in X? So what's the change in negative 4 to 1? 5. From 1 to 4, 3. Can we do it in our head? 25 and 9, 34, and just say square root of 34. That's what we want. Right? There's no need for me to write all this stuff out. If you know what you're looking at, just take it. X squared minus 10 equals 3x. Yesterday in class, we said you got to get your variables together. So bring minus 3x to the other side, minus 10 equals 0, and hope you can factor it. Oh, by golly, we can. X minus 5 times x plus 2 equals 0. One of my answers is 5, the other is negative 2. Okay, now we're looking at minus 9 halves x minus 5 squared plus 7. I don't know if I'm setting this to 0 or what I'm doing. Let's find out. Two values of correspondence. So I want to name 2 points on this curve. I know I've got that happened. Okay, so what do I see? What do I see? I see that in order to get a 2 here, I need something squared, so I need the square root of 2, but I see the vertex 5, 7. And I can see that if I use 5 plus root 2, and I get rid of the 5, if I get rid of the 5s, I've got root 2, and root 2 squared is 2, and that's going to get me minus 9 plus 7 minus 2. So that's a little tricky one. All right, if I go over root 2, if I put 5 plus root 2 here, hopefully you can see the 5s cancel. And what's the square root of 2 squared? 2. What happens to the 2's? Cancel. And minus 9 plus 7 minus 2. So that's going to give people a hard time. But we'll see if, with some practice, that we spot it and deal with it easily the next time we see it. All right, so now we're writing a product, 5m squared, y to the fifth, minus 15m y8. As a product, what do 5 and 15 have in common? 5. What do m squared and m have in common? M. Y to the 5, y to the 8th, y to the 5. And now I got to build it back up to these two terms. Looks like I'm missing an m. I got the 5. Looks like I'm missing an m. I got the y to 5, so that's good. Missing a 3. I got the m. y5 to y8. Looks like I need 3 more. I'll be talking about this type of problem less and less as we go through lesson sets now. So I'm just going to write answers from now on. Save some time. Y equals 5. So now, instead of a picture, you've been given the same exponential situation, but it's coming to you as data. 24 gets us 11. So write the exponential function that passes through these 2 points and has that as an asymptote. I might ask, what's the base of this exponential function? As a first question, since I was talking about it 10 minutes ago. And you're pausing the video as you go along, I hope. How do you get from 5 to 8? You change by 3. How do you get from 5 to 11? You change by 6. So there's a little bit of a doubling process in this. Starting at 5, getting to 8 means time addition of 3. Getting from 5 to 11 means I need the number 6. And starting at 1993 and changing by 7 and 24, 31 years. And then I've got that exponential function. And we're going to be moving into compound interest, which is an exponential calculation and things like that soon. In fact, we're going to be heading towards e to the x real soon. But it takes practice for us to get to e to the x, and we're doing that practice right now. 5 log, maybe I'm graphing this one, log base 2, probably graphing this, x minus 7 over 3 plus 4. Let's see, that's problem number 39. Name 2 coordinates. I'm just going to graph this. You're going to see the 2 coordinates show up anyway. So logarithms have differentials as bases, but instead of vertical, if we switch the x's and y's, they're horizontal. So I'm going to get the distance of 1 and a distance of 2, and I'm going to get a graph that looks like that, but I have to know where it starts from. And I know it starts from 7. That's the critical number. And if I go over 1, 8 should get me a nice simple number to work with. 8 might, no, it doesn't. 2 to 1. Oh, this was a 3. I'm sorry, I misread this. Going back. So my first jump should be 3 units over, and then my next to get a 2 should be 6. All right, so that's what I see. I wonder if I'm doing the inverse of the previous problem. And I snuck that in on you. No, I didn't. No, not similar at all. Okay, so if I go over 3 from 7, then 10 was the nice number to work with. So let's put 10 in here. 10 minus 7, 3 divided by 3 is 1. We talked about that earlier in the lesson set. I want you getting real familiar with what the exponent is that gets you a 1. It's 0. And 0 times anything is 0. You get this answer every single time. If you make that a 1, you're going to get the constant. Look for that pattern as you go along. The next one is going to be 5 plus 4 is 9. Okay. So what number do I want? 6 plus 7, I believe 13. So 13 minus 7 is 6. And 6 divided by 3 is 2. And if you ask the question, what do you put on top of a 2 to get a 2? I hope you say 1. And 1 times 5 plus 4 is 9. We're going to be practicing that process. And each time we practice it, I hope you give it your attention and you get a little better, a little stronger, a little quicker. Okay. So it's all about set the parentheses to 0. When you're doing logarithms, set the argument to 0. Set the argument to 1. Set the argument to the base, and you can graph logs in 10 seconds or less. I had somebody erase me one time 20 years ago. He almost beat me. I was proud. I hung in there. That kid got it down to like 5 seconds. And I say, we had to go. I still had done more practice than him. All right. 2x squared minus 8x. And I'll uphold the pride of the teaching fraternity. What am I doing with it? Finding the roots. Okay, if I'm finding the roots, do I want to factor that? Probably, I don't, at this stage of the game, I don't want to think. So I'm going to do 2x minus, I know if they're opposites, it's a minus. 8 divided by 4 is 2, 2 squared. If I put a 0 in, that gets me 4, 8. I don't want that 8, I want 9. Now I'll set that to 0, and I've got -1 on this side. I've got 1/2 here, and then I've got 2 plus or minus, and I know the square root of a half is √2. So I hope I'm right. Could it have been factored? Probably, because I usually give you something other than, and then I'll check to see if I butchered that. So 3's, I don't see 3's working. 1 and 9, 9 and 1, I don't see that working. So b squared minus 4ac, this is the one time I do this, 4 squared, b squared, that minus 4 times a is 2 times 9. So we got 72, so minus 8, yeah. So I believe this is correct because those are imaginary roots. All right, and did I get imaginary? I didn't get an imaginary here. Did I make a mistake? Oh, I forgot the minus sign there. All right, so that's why it's nice to do things from different perspectives. And since you got the square root of minus 8, we might as well work with it, right? That would have been inside the square root. Minus 8 would have been out here. 2a, 2 times 2 is 4. Well, 4 goes into 8 twice, so that checks that off. This is the square root of 4 times the square root of 2. Square root of 4 times the square root of 2. And that's 2√2. Minus 2√2 over 4. I did butcher this a little bit, didn't I? Yeah, so I forgot the half here. So something went wrong here. So -1, and I'm not going to do this video again, so maybe I can spot it real quick. Minus b over 2a, 8 divided by 4 is 2, so this is correct. Dropping in a 2, minus 16, dropping in the 2. Cut in half, minus 8 plus 9, so that's correct. So 1 is correct. Bringing it over, -1 is correct. The a term is 2, so that is correct. And then I'm taking plus minus the square root of that. I believe that's still correct. So I might have made a mistake over here. But at this stage, I am going to continue. And I will look at it later myself because I don't like to end a problem that way. But in there is the process for doing it. So 20x to the 4 equals 5x squared. And so that gets us, bring that to this side. So you're subtracting, setting it to 0. Anytime you have something, you got to get your x's together. When you solve equations, you got to get your variables together. And it's nice if you can write sums and differences as products that equal 0. And in this case, we can. So 5x squared is common to both terms. I need a 4 and an x squared here. And I need a -1 here. That equals 0. This is a difference of 2 squares, 2x plus 1 times 2x minus 1. It's nice to see that. And this is 5x squared. So now we have one of those strings that equals 0. So one of my answers could be 0. That's a double root if you're graphing. -1/2 comes out of that parentheses. +1/2 comes out of that parentheses. So that looks okay. Going to speed this up a little bit because this is going on forever. And students might come into the room at the pace I'm going. So log base 5 to the 9, b to the 9. B to the 9, b squared, and I'll just tell you what your answer is. It's 2 over 9. And now I'll show you how you could get it. Now, well, you don't need any work. We don't want something to the 9. We want it to the 2. What gets something to the 9th power out? √9. Okay, so this is really b to the 9 to what exponent equals b to the 2? Well, 9x has to equal 2. So you've got to get rid of that 9 operation is exponentiating. So you get rid of exponentiating with a root. Right? What gets rid of squaring? Square rooting. Gets rid of cubing? Cube rooting. What gets rid of ninth powering? Ninth rooting. Okay, so that was a 2-second question if you understand the concept. And then just write it on your answer key. Where the heck am I? Log, I think I skipped one. Log base M of M, the M&Ms, I like M&Ms. Yeah, and they are to the -2. Okay, so we're looking for exponential activity. Well, the first thing I see is, why don't I express that exponentially? And that's M to the 5. And is there a way that I can express that as one number? Yes, -10. So what's log base M of M to the -10? -10. And I hope that highlights the fact that you're looking for exponents, exponential activity on top of M. I have boiled it down to -10. Yes, it's definitely maple syrup time. Gonna be boiling that sap here soon. All right, -2. X -3 squared -5 equals 0. We're trying to make the connection that if you have the vertex and you have the A term, that's all you need to answer the following question, which is going to be 3 plus or minus the square root of 5 over -2, which makes this imaginary, I believe. And I did that quickly. I'm getting tired, so let me double check here. So -5 becomes +5. -5 over 2, yes. So therefore we have plus minus the square root of 5/2. And the last thing we do is add 3. That should become familiar to you if you've done all the other lesson sets. Should be getting to the point where you could do that easily, I hope. Certainly possible. Okay. Where am I? 46. I don't know what 46 is. Not that well prepared. Oh yeah, something new. A new problem that I just want to make sure everybody handle. It's a pain. It's not the most fun, but necessary. Because some folks might make some conceptual mistakes or mechanical mistakes that we want to try to practice not doing. All right, I like to do these in columns. It's all about like terms. Okay, and can we add x squared plus x equals x cubed? Can we do something like that? And the answer obviously is no. And how do we check it? With a number. Let's use 10. 10 squared is 100. 100 plus 10. If I'm not mistaken, that is not equal to 1,000. All right, so we can't add like terms, unlike terms. And we're going to get a lot of unlike terms, but we're going to get a lot of like terms. Is x cubed plus x cubed 2x cubes? I hope I don't have to explain that because that is true. All right, minus 2x to the 4th times x squared gets me minus 2x to the 6th. Minus 2x squared minus 3x is positive 6x to the 5. I actually have to think about what I'm doing here. Minus 8x to the 4th. Now, minus 5x squared times x squared is an x to the 4th. It's minus 5x to the 4th. I'm going to put it here. Minus 5x squared times minus x is positive 5x to the 3rd. And minus 5x squared times minus 6 is positive 30x squared. I hope I'm not making any mistakes, but now I'm going to, this one, it's only got one column here that's alike, but so minus 2x to the 6th plus 6x to the 5th minus 13x to the 4th. Just put it in columns. You'll see that in future problems we'll have more columns that you add up more easily. And it's just easier to keep track of things, I think, or I wouldn't be telling you to do it that way. So if somebody finds a shorter way to do it, write to me, please, because the rule in my class is the easiest way we can do something, we're going to adopt. All right. Oh, I did have that problem over there. 4/5 plus 2i. And in the Last lesson set, I think I told you the shortcut for getting the denominator is 29. Okay, you're gonna do it out. So we got 5 minus 2i is the conjugate. 5 minus 2i is the conjugate. So in the numerator, we have 20 minus 8i. In the denominator, we get 25 plus 10i minus 10i. And we've got minus 4i squared. Yeah, what always happens to the middle terms? Always gone. A conjugate, a minus times a plus is always a minus. It's always a minus. And what does I squared do to the minus? Changes it to 4, positive 4, and 25 plus 4 is 29. So that's just a little shortcut. Saves you having to work. If you look at answers and you check it, the original question out, a lot of times you can see answers that just, okay, so 4i to the 10th, we use I squared in my class. And it looks like we're doing that 5 times. And I think it's really important that students know what -1 to the 5 is. It stays negative. So our answer is -4. Okay, x to the 4th equals -16. This problem has stumped me. All right, x to the 4th equals -16. I just basically looked at x squared equals -16, which is a parabola. Right, and the answers to that are plus or minus 4i, right? So I just assumed plus or minus 2i, but then, I to the 4th is +1. So this, I haven't thought about it since putting this on the board last night before I went home. But I got to give this some thought. I'm not quite sure where we're going with that. I did, as I was sleeping last night, I obviously wasn't sleeping because I woke up thinking about this problem. And I did a little calculus. And I got to 12x squared and looked at the acceleration. Anyway, I'm on hold here. I've got to do some real thinking. And if somebody out there wants to write about it, please do, because it's got me. It's a Math Olympiad problem, so got to work with it. At least I think it is. So 3x minus 2 over 5. What the heck am I doing with that? Number 50. Getting there. Oh, I didn't write the whole problem. 3x minus 2 over 5. So this is something new we did yesterday. I'll call it bingo, bango, bongo. And I'll put that in the, I'll write that in the YouTube paragraph there. That there's this new problem, number 50. Minus 4x minus 1 over 2. Now let's just look at a quick subtraction. Let's look at 6/5 minus 5/5. No, I don't want to do 5/5. Let's do 6/5. Yeah, I do want to do 5/5, but let's do it 6/5 minus 2/2. Let's do that. All right, so 6/5 minus 1 is really 1/5. We know our answer is going to be 1/5. So bingo, bango, bongo is really all about just filling in these 3 parentheses. That's all it is. Fill in those 3 parentheses. Now, why can I do that? Because textbook would say to get the common denominator, you multiply by 2, multiply by 2. Well, can't I see 6 times 2 here? Can't I see 6 times 2 there? Can't I see putting the 5 here, 2 times 5 there, 2 times 5 there? And can't I see 5 times 2 is 10? So 12 minus 10 is 2/10. And then you reduce it. 2/10 is 1/5. So that's what I call bingo, bango, bongo. And students always make sign errors when they first do this. I very rarely get a student who gets this right coming out of Algebra 1. So let's do bingo minus bango over bongo, which we know is 10, and I don't even need to write that, right? Bingo is 3x minus 2 times 2, which is 6x minus 4. I don't even need to write that eventually. But I suggest you do that until you get this down pat. This is the one that really matters. 20x minus 5. And students always butcher minus a minus 5, unless it's in parentheses. Okay, so what's the final answer? Well, 6x minus 20x, I'll write it up here. 6x minus 20x minus 14x minus 4 minus a minus 5 is plus 1 over 10. let's check our answer. What would be an easy number to work with here? I erased the original. All right, let's not check our answers. Just assume I didn't make a mistake at this stage, because we'll be practicing that the rest of the term. All right, where am I? 51. Graphing, finally. So y minus 3 equals negative 2/5. X plus 7. 2-point problem on the test today. Maybe people aren't able to get all these problems done in 70 minutes. And that's probably the case because this was left blank. And I don't see why, because we should be able to see a negative 7 gets us a positive 3, especially if you bring the minus 3 to the other side, right? People were able to tell me 3 coordinates. Well, if you can show 3 points on a line, you should be able to connect them. So I'll change by 5, minus 2, go down 2, 1. So where's negative 7, 3? Let's call that negative 7, 3. Let's call this negative 2, 1. Looks like it, if I took a little more time, but that's the general vicinity. So graph paper would have been nice there, but that's okay. Minus 4x squared. We're going to graph this parabola. Minus 4x squared minus 16x plus 3. How much information do we need? We need the vertex. Okay. I know 0, 3 is on this side, but we can find it after we get the vertex to corroborate. Minus b, 16 divided by 2a, minus 8, minus 2. Yes, we're on the downward side. Put some arrows here. Yeah, Milo would tell me put some arrows there. All right, put a negative 2 in, and we should get the 2-to-1 ratio. So that's minus 16. This had better be 32 plus 3. It is. So 16 plus 3 is 19. And that's it. There's the graph. The squared change is 4. I've gone down 16. And coincidentally, that happens to be the same as that coefficient. No coincidence. All right. Almost done here. Wow. I think the sun is about setting. It was just coming up a little while ago, and it looks like it's about to set. Minus 3 square root of 2x minus 4 plus 7. I have a square root that starts somewhere and goes down. And boy, wouldn't it be nice if we had the square root of x minus h plus k equaling a times the square root of 0 plus k? I would hope that's what we're looking for, because that's the smallest square root you can have. So x is 2, and that gets me a 7. Now, what's a nice, easy number to work with? Well, how about the square root of 20? Oh, let's do an even square root. How about the square root of 16? I know the square root of 16. I wonder if I can figure out the number 2x minus 4 that would give me 16, because then I could do another point on the curve. All right, so when does 2x minus 4 equal 16? How about doing that in your head this time and saying 10? Okay, and what is the square root of 16? 4 times negative 3, negative 12, plus 7, negative 5. Okay, wow, that's that graph. Now, if you want to find more points to prove the trajectory, probably should, because I have people that will graph it concave down, not concave up, and that's a misunderstanding of the square root function. Takes bigger and bigger area to go up by 1. 9, square root of 9, 3, square root of 16, 4, square root of 25, 5, square root of 36. By golly, it takes more values, more area to just get that 1 unit of change. Slow growth, but in this case, slow decline because of the minus 3. Boy, am I rambling now. 5 times 3 to the x minus 4 plus 7. I want to get 3 to the 0, and I want to get 3 to the 1. And I see an exponential growth where y equals 7. I think my first jump is going to be 5. I think my next jump is going to be 15. And then the next jump, 45. And I think I'm looking like that. And if I want a 0, then I want a 4. And 4 plus 5 is going to get me 9. And if I want a 1, I want a 5. I hate the fact that I've given you anything that repeats here. 5 gets me 15 plus 7, 22. Okay, and it's seeing these differentials that really matter. Okay, so on my first differential, right there. Second one is that times that. And then the next one would be another 3 times that, so on and so forth. That's why it's growing exponentially. Last problem. My God, I hope my battery doesn't give out. 200 plus 20. Why am I giving it plus 20? It looks similar. Log. Oh, God, it's language, and you're just trying to learn it. And I gave a 2. X minus 7 over 5. And I talked about the parentheses. Can you remember from 20 minutes ago what I want that parentheses to equal? I want it to equal 0. I want it to equal 1, and I want it to equal the base. So what do I see? When does it equal 0? When x is 7. Maybe it's the same problem we did before. I know I'm going to get the inverse of growth, and I'll show you that on the next lesson set with some drawings. Yeah, it's real quick and easy to show some drawings. I don't have a dark enough marker to do it right now. All right, so I'm going to change by 5, and then I'm going to change by 10. Those are the differentials hiding in this problem. And if I change by 5, 12 should give me a 1 in the parentheses. Let's put it in and find out. 12 minus 7, 5 divided by 5, 1. Why do we want 1? Because I hope we're getting better at log 1 regardless of the base. Yes, you're right, that's 0, which gets me 200. The next one's going to be 220. If we find the right number, that gets me 2. Well, 5 times 2 is 10. 10 plus 7 is 17. So 17 should get me 220. Let's put it in and find out. 17 minus 7, 10. 10 divided by 5, 2. What's the exponent you put on top of a 2 to get a 2? I'd love to multiply the number 20 by 1 to get 220. And now that's going to take some practice, but just a couple of minutes a day. You know, if we do that every day, if you look at it every day, think about it every day, practice it every day, then 2 minutes a day in 8 minutes, you should be able to do that pretty darn quickly. That's what you need to do. All right, so that's a lecture to my class. Okay, I'm out of breath. I hope that makes a day of practice for someone who can't get into a classroom. All right, have a good day, everybody. Oh, I don't want to end the meeting yet. I'm having fun meeting people all over the world now. Oh, my Lord. I met Yasser the other day. There's another gentleman, you know, folks my age, getting back into high school math. I'm overjoyed, you know, so feel free to say hi. And Saladin, if you ever come back and watch these, I certainly was happy to chat. All right, everybody, have a good day.